In this lecture, we're going to talk about a trail, a path, a cycle, an Eulerian trail. And we're also going to look at two important theorems. One is a theorem about bipartite graphs, and the other is a theorem that allows us to find an edge decomposition of a closed trail. Now, we've seen this diagram before when we talked about the number of trails from C to D. And we saw that we could go from C to A to B, to C to A to B, to C to A, and then finally to D. But of course, this wasn't the shortest way. We could have just gone from C to A to D. Now, what are we doing here? Isn't it obvious that we can just go from C to A to D? Well, what we're doing is we want to generalize this concept that if we have a walk from a vertex U to a vertex V, and that walk contains a closed trail, then we can delete that closed trail and still go from U to V. So if you have a very large graph, say thousands of vertices, and you're writing a computer program to find the shortest walk, then perhaps you want to include in your program to search for closed walks that can be deleted. So now we're going to define a trail, a path, and a cycle. A trail is a walk with no repeated edges. And a path is a walk with no repeated vertices. So a closed path, that means we have a closed walk with no repeated vertices. We call that a cycle. Now suppose that we want a UV path. That means you have a walk from U to V that does not repeat any vertices. So suppose that's what you want, a UV path. And you have a UV walk, but what you want is a UV path. Well, if you have a UV walk, then by lemma 1.5.1, you know that it is either a path, and you have what you want, or it contains a closed subwalk. So from the preceding slide, we know we can delete that closed subwalk without changing the ability to go from U to V. So this leads us to the theorem. Every open UV walk is either a UV path or can be reduced to a UV path. So a cycle is a closed path. Now recall that a path does not allow you to repeat any vertices. And the fact that it's closed is you return to the same vertex from which you started. A cycle is said to be even if the number of vertices is even. So we have an interesting theorem connecting bipartite graphs and even cycles. A graph is said to be bipartite if and only if it has no cycles of odd length. So anytime you find a cycle in the graph, if it's even, if a graph has this property that all its cycles are even, then it's bipartite. But if it has just one odd cycle, then it's not bipartite. What if it has no cycles? Then what would we say? We used this graph previously to discuss walks on graphs, and notice that it has no cycles. You could say by default that it has no odd cycles if it has no cycles, so the theorem applies. Or you could say all of its cycles are of length 0, and 0 is an even number. So clearly, a graph with no cycles is bipartite. Since it's bipartite, there is a partition of the vertex set such that all the edges run between the vertex sets and none of the edges are inside each set. So do you see the partition of the vertex set? That is, can you partition the vertex set into two sets, say U and W, where there are no edges in U and no edges in W? Here is the partition. Since 2 and 4 are not adjacent, and 1, 3, 5, and 6 are all pairwise non-adjacent. We can think of a closed trail as starting at a vertex and traversing edges until you return to that starting vertex. And because it's a trail, not a walk, because it's a trail, that means we're not repeating any edges. So we have an edge set associated with our trail. We're going to define what we mean by decomposition of a closed trail. A decomposition of the closed trail is a partition of the edge set, excuse me, a partition of the edge set. And recall what a partition is. A partition of a set is a collection of subsets that are disjoint, and their union is the entire set. So a decomposition of a closed trail is a partition of the edge set with the property that each set in the partition induces a cycle. So for example, let's look at the closed trail where we start at the vertex 2. We go from A to C to E to H to D to K, returning to 2. Now, the decomposition of this closed trail is the set of edges A, C, K, which induces one cycle, and the set of edges D, E, H, which also induces a cycle. Notice that on the closed trail, we go from A to C to E. So E follows C, or E is incident to C. But in the decomposition, C and E are in different sets of the partition, because once again, A, C, K is one cycle, and D, E, H is another. So we have the following definitions. An Eulerian trail in a graph is a trail that contains every edge of that graph. And an Eulerian tour is a closed Eulerian trail. A graph that contains an Eulerian tour is called an Eulerian graph. So can we find an Eulerian tour for Peterson's graph? Now recall, we want to visit every edge exactly once. We could try visiting the edges on the outside cycle first, and then visiting the edges on the inside star. But then, what about the edges connecting the cycle to the star? So that won't work because we can't visit those without repeating some edges. So perhaps we should alternate. That is, start at the vertex at the top and go to a vertex on the star, traverse an edge there, and then go back out, traverse an edge on the cycle, and then go back in, traverse an edge on the star, and then go back out. Now, eventually, I think I'm going to be in trouble. But perhaps it's just I'm not being clever. But I don't think that we can find a tour that uses every edge once and only once. Because if you look at the vertex of degree 3, which is all of them, but if you're at a vertex and it's of degree 3, suppose you think of one is coming into that vertex and one is going out on your tour. That leaves the third one. Is it coming in or going out? In either case, we're going to have to repeat one of the edges to continue our tour, unless that's the last, both the first and the last. However, all the vertices here are of degree 3. So I think we're going to wind up being trapped at a vertex, not being able to leave without repeating an edge. So here's another graph. Perhaps we'll be more lucky here. Is this an Eulerian graph? Can we traverse every edge once and only once? I wonder if we can do this in alphabetical order. So we'll start with A, B. Yes, we can go to C, and then D. We can follow D with E, and F, and G, up to H, I, J, and K, and back to where we started. So we not only have an Eulerian trail, we have an Eulerian tour. We return to where we started, so this is an Eulerian graph. Notice that we did repeat vertices, but we did not repeat any edges. So, in this lecture, we defined what a trail is, what a path is, what a cycle is, and what an Eulerian trail, tour, and what is an Eulerian graph. We know that we can characterize bipartite graphs with even cycles, and we know that we can decompose the edge set of a closed trail into disjoint cycles.